Hello everyone, this video's topic is diamond silicon vacancy, and here I will do a presentation to introduce the paper Single Photon Switching and Entanglement of Solid-State Qubits in an Integrated Nanophotonic System, which is published in 2016. I hope my interpretation will help you to have a general understanding of the frontier work of this paper. Okay, let's get started. First, I want to explain why I chose this topic. We have deep understanding of MV Center after half semesters learning, and now we are familiar with the level structure and its application in quantum engineering. Although it has many advantages, as the paper said, but also some flaws are mentioned. I want to do a transverse study to see what are the common properties of this type of materials and in what else application can this structure in diamond be used. This paper is about the technologies and applications based on Silicon Vacancy Center. Now, let's talk about the motivation and context of this paper. We need to know that an integrated platform of scalable quantum nanophotonics is very important for application in quantum science, such as quantum computing, quantum chips, and quantum communications. And efficient interfaces between photons and quantum emitters is the key for the integrated platform of scalable quantum nanophotonics. Also, there are great challenges to realize such an integrated quantum platform in solid-state systems, and this work presented an architecture by integrating silicon vacancy color centers in diamond nanophotonics devices to overcome these challenges. So, what challenges need to be overcome? I think there is a big challenge in overall goal and some difficulties in implementation. The outstanding challenge is weak interaction between single photons and individual quantum emitters in solid-state systems. That means how to make the multiple qubits strongly coupled for constructing an integrated quantum device. And the difficulty includes the random positions of the quantum emitters in solid-state systems, which makes the realization of scalable devices with multiple emitters difficult. And how to suppress the effect of destroying quantum coherence of the coupled qubit systems, such as inhomogeneous distribution, rapid decoherence, and significant spectral diffusion in optical transitions. Then we were curious about what are the advantages of the diamond integrated platform with silicon vacancy centers. According to the paper, its advantages are very attractive. First, it is facilitated to realize the strong coupling between single photons and the silicon vacancy centers in diamond photonic crystal cavity. What's more, the positions of the silicon vacancy centers can be precisely implanted into diamond waveguide or photonics crystal cavities. Also, the effect of inhomogeneous distribution, rapid decoherence, and the significant spectral diffusion in optical transition can be greatly suppressed due to the invergent symmetry of the silicon vacancy center, which result in the nearly lifetime broadened line-wise. Now, we can go to the second part, technical assessment, including the main results and which technologies and methods are used in the experiment in this paper. The authors explain these results separately under each subtitles to show the method and the technology details. I think the fabrication process and the experiment involve lots of optics knowledge, which I learned in my undergraduate, and I know it's not wise to explain each concept and principle that are mentioned. I would try to simplify the details and focus on the main process. The first question is, how to fabricate a diamond integrated platform with silicon vacancy centers? Here are the keys. Technique 1, the angled reactive ion etching is applied to fabricate a one-dimensional waveguide and the photonic crystal cavities. Technique 2, the focused silicon ion beam implantation is applied to deterministically position at the center of each cavity for optimal coupling between an individual silicon vacancy center and the cavity mode. Technique 3, the annealing processing at 1200 Celsius degree in vacuum is utilized to form the silicon vacancy centers and mitigate crystal damage. Figure 1 shows positioning and strong coupling of silicon vacancy centers in diamond cavities. Next, what can the diamond integrated platform with silicon vacancy centers do? Here are the functions of the platform with silicon vacancy centers. Function 1 is realization of quantum optical switch between the transmission and fluorescence emission based on a single silicon vacancy center at single photon level. We can see they made an all-optical switch with memory by optical controlling the metastable orbital state of a single silicon vacancy in Figure 2. The energy level structure and the preparation method of initial state is very similar to MV Center. Use gate pause to choose state C or state U as the initial state. In the Figure 2C, we see that when state U is the initial state, the probe pulse will have high transmission rate and low fluorescence rate. If the initial state is state C, it's the opposite. So this is the switch. They also did an experiment to verify optical switching at the single photon level by using photon correlation. As the Figure 3 shows, the key point is the value of G2, the second order correlation function in Figure 2b. If we don't understand this function, it doesn't matter. We only need to know it can be used to determine whether the scattered photons are single photon emission. In general, when this value is less than 0.5, we can assume that it is at single photon level. The result in this paper is 0.15, so it is a good result. And function 2 is that it can use Raman transition to realize tunable single photon source. Although in this system, the bandwidth was suppressed by some of the previous techniques, some uncertainties in the fabrication process still resulted in a relatively broad bandwidth of fluorescence spectra. So, how to solve this problem? The answer is Raman transition. From the Figure 4b and Figure 4c, we can see the not real state. It has the delta difference with resonance frequency here. This is the magical place of Raman transition. The bandwidth of R is narrower than the fluorescence peak. Moreover, the Raman photon frequency can be controlled by controlling the Raman laser light intensity to control the bandwidth, which means the spectrally tunable single photons are realized by using Raman transitions. Function 3 is the realization of entanglement of silicon vacancy centers in a diamond nanophotonic. Waveguide by utilizing an efficient probabilistic entanglement generation scheme based on detection of indistinguishable photons. Figure 5d gives a comparison of the second-order correlation function between single set-count vacancy, the generate state, and entangled state. The red line means generating two photons at the same time through entangled state here. At last, what can we do to improve these technologies? The first thing is increasing the coherent time, such as operating at low temperatures or engineering the photonic density of states to suppress photon relaxation processes. The second is improving nanophotonics design using slow light waveguides and cavities with higher Q ratios. Furthermore, the efficient fiber diamond waveguide coupling for improving the efficiency, even exceeding 95%. For applications, first, their work shows possibilities for realizing large-scale systems involving multiple emitters strongly interacting via photons. And because of the large cavity bandwidth, more than 10 coupled emitters can be addressed independently in a single cavity to form complex quantum nodes that efficiently couple to a fiber network. So such a system will pave the way for the realization of integrated quantum networks with applications such as long-distance quantum communication. And that's all. Thank you.